Okay, the other type of dating that we're going to talk about, this one's a lot more accurate. This one gives us a numerical age. So unlike relative dating, where it only gives us if something is younger or older than that particular layer, absolute dating is going to give us a numerical age for the fossil. So we're going to be able to tell how old that fossil is. So what we might do is we might date the surrounding rocks, or we might date the fossil itself. And the process that we use to come up with an absolute, so this is a numerical value, is the same, whether or not it's the fossil itself or the rocks surrounding the fossil. So first, some other words that you might find for absolute dating is it might be called radiometric dating. Now, this is a bit of physics, but hopefully we can get through physics. I think you also cover it in maths as well. So we will be practicing this in class. I'm just going to go through it briefly, and then we'll see how you go in class as well. So what we do is we use what we call radioactive isotopes of certain elements. So what happens is carbon, for example, exists in two different forms. Okay, so carbon exists as a bunch of carbon-14. Yeah, so we're just going to say carbon-14, and the organism will die, and it will have a certain proportion of carbon-14. So that'll be whatever you don't need to know it, yeah, but it'll have a certain proportion because it's got all this carbon that comes in and out of its body, and it's a certain amount. Now, over time, carbon-14 doesn't like to stay like carbon-14, and it likes to break down into this substance called nitrogen-14. And what you can do is you can figure out what is the ratio of carbon-14 to nitrogen-14. Yeah, so that's the biggest thing here. We're going to figure out the ratio of one element to another element. So it starts off as carbon-14, not very stable, breaks down over time into nitrogen-14. Now, the good thing is we know how long that takes. So we know what we call the half-life of carbon-14. So the half-life of carbon-14 is actually about 5,700 years. And it means that in 5,000, I'm going to write this down now. So in 5,700 years, yeah, 50% of carbon-14 will become nitrogen-14. Okay, and that is equal to 1/2 life. Okay, now if we go another 57,000 years, 5,700 years, another 50% of that will become nitrogen-14. So now 50% of what's left will go from carbon-14 to nitrogen-14. All right, so here is our initial here, and we've gone 1/2 life, so 1/2 life, and we've broken down 50% of my carbon-14 has become nitrogen-14. After another half-life, so that's already broken. Actually, I've done it the wrong way, wrong color. That won't help me. All right, so 50% has become nitrogen-14. Doesn't matter what the symbol is. I'll get there in a minute. So in the second, let's try again. So here is original. It is 100% carbon-14. After 1/2 life, we get 50% has become nitrogen and 50% is still carbon. After 2 half-lives, so this is after another half-life, half of what is left becomes nitrogen again. So now we end up with 25% carbon and 75% nitrogen. Now, if I went down and went to a third half-life, you would get that. So you've still got your 75, and now you've got it broken down again, and that's another half. So this becomes 12.5% carbon at the end of that. And that's going to keep going after 4 half-lives. I'm just drawing this a bit bigger. We now get half of that 12.5% left, which is 6.25%. And what we can do is we can actually measure that percentage of carbon in a rock or in a particular fossil, and we can use that to determine how old it is. And I'm going to show you that using our simulation during class today. So what we do is you find out your ratio. Now, you should be given that ratio. You shouldn't have to calculate that ratio. We'll see how we go with a couple of my questions. And we can use that to calculate how many half-lives have elapsed. So if you have 25% left, that means it's gone down to 50, and then it's gone down to 25. So 2 half-lives have passed. Then you can multiply that number of half-lives by the known half-life of the element. So I said in the case of carbon, that's going to be 5,700. And so you multiply that by 2, and that's going to give you the age of the fossil is going to be 1,140 years old. Oh, sorry, 11,400 years old. Okay, so it's a little bit of maths. We're going to work through some examples here, but essentially half-life is this definition here. It says it's the time required for the amount of the radioactive material to decrease by 1/2. Now, there are 3 of those that you need to remember. Now, you don't need to remember the numbers. So you don't need to remember specific numbers. No specific numbers. All I want you to remember is this fact here. Carbon dating is only reliable for fossils up to 50,000 years old. Anything older than 50,000 years old, this is no good. Now, you must use one of the other types of dating. So what are the 3 types of dating? So the 3 examples that you must know that carbon dating happens, and that's useful for things that are less than 50,000 years old. And then if anything is older than 50,000 years old, we can use uranium lead dating or potassium argon. Now, what that means is they are just different radioactive elements. So these are these forms of dating, uranium lead dating and potassium argon dating. These are good for things that are older than 50,000 years. So look at the question. We'll have a look at a few in class. If anything is older than 50,000 years, then you would use uranium lead or potassium argon dating. And anything younger than 50,000 years, you can use carbon dating. That's the extent that we need to be knowing it for. And you will see where that comes when we get there. So what it means by this is carbon dating, and carbon breaks down into nitrogen-14, like I said. Uranium lead dating is the uranium decays down to lead. Potassium argon, the potassium in the organism or the rock decays down to argon. And that's how you do it. So let's just run through one little example. This is the example in your notes on page 10. So analysis of a fossil shows the proportion of carbon-14 is now 1/8 of what it was. So this means 1/8 that is left is carbon-14. So what are we going to do? So what we can do is we can go, all right, after 1 half-life goes to a half, after 2 half-lives goes to a quarter, and after 3 half-lives it goes to an eighth. So this is 1 half-life, this is 2 half-lives, lives. This is 3 half-lives. So when someone asks you, how did I get to an eighth, or how did an eighth become 3 half-lives, I just do this little process. That's it. There we go. As 1 half-life for carbon-14, and they would have to give you this, okay? So they would have to be given in the question. We multiply the number of half-lives by the half-life of the element. So we do 3 because there are 3 half-lives passed, multiplied by the half-life being 5,730, and we get this age here, 17,190 years old. So that is how you might use half-life to calculate something. There's an example of an actual question. So in 2006, 2 separate paleontology laboratories were set up in the Sahara Desert. Lab 1 uncovered a burial site that contained human remains. Over 200 human remains were found, and they were dated between 10,000 to 4,500 years ago. In Lab 2, they discovered a 110 million year old plant-eating dinosaur, Nigersaurus, in a different sedimentary layer, so a different layer. So automatically, what I'm thinking is, the first one, if they have this absolute numerical value and it's less than 50,000, that must be carbon dating. So I'm not even going to read the question yet. This one here must be potassium, argon, or uranium, lead dating. And the fact that it's in a different sedimentary layer means to me that you're also able to do some relative dating on that as well. Let's have a look at our phrases here and see what we can get through. So to date the fossils accurately. So we want to know accurately. They would most likely have used carbon-14 dating for both the human and the dinosaur. Now remember, it can't be for the dinosaur because the dinosaurs are too old. They have to be younger than 50,000 years. So uranium dating for both the human and the dinosaur remains. The humans are too young. Yeah, we wouldn't use uranium lead dating for them. Uranium-235, which is the same as uranium lead dating for the humans, and carbon for the dinosaurs. No, it's actually the other way around. So carbon for the humans, yes, and uranium for the dinosaurs, yes. And so we get an answer of D. So I know that you might have got a little bit confused about half-life. Often it becomes a bit of a source of confusion. I want us to get it, so we're going to go through some examples in class as well, but you can see the actual questions that they're asking you, not too difficult in terms of it. Remember, you don't get a calculator, so they can't ask you anything too hard. And that's the end of my little video on Half-Life.